Our next presentation is by Martin Aberg from Cobham Gaisler, and he is going to be talking about Zephyr RTOS LEON and NOEL-V processor support status. I'm not sure if that's NOEL-V or NOEL-V, but all right, Martin, thanks.
Yes, can you hear me?
Yes, we can hear you.
Yeah, excellent. So, hi, my name is Martin, and I'm here from Cobham Gaisler. This presentation is about the LEON processor support in the Zephyr real-time operating system. The next slide, please. I will start with a short introduction to the LEON-3 processor, and I will give an overview of the Zephyr RTOS and continue by describing the LEON integration. So next slide, please. We at Cobham Gaisler try to be a one-stop shop for system-on-chip solutions. And at the heart of the company, we have our synthesizable IP library that contains processor IP cores and also peripherals that allows us and our customers to build a complete system on chips. We ourselves use this IP library to design components that are primarily radiation hardened and fault tolerant, targeted towards the space industry. We put these components and also FPGAs on development boards to make it convenient for users to start designing software. We provide simulators and debuggers, and we also provide the compilers and operating systems, including Linux, Artems, bare metal, and commercial options such as VxWorks from WindRiver. And we are also adding Zephyr to the set of supported operating systems to fill the lowest footprint segment. The IP library is named grlib and is available under GPL or commercial license. It contains two lines of processor products, the LEON processors, which implement the Spark architecture, and the NOEL-V processor, which implements the RISC-V architecture. So next slide, please. Our products are today primarily used in the space industry, where the LEON processor has populated large parts of the solar system, either as ready-made components or as IP cores that have been integrated by our customers into system-on-chip designs. So next slide, please. Our main processor product is the LEON-3 processor. It's a 32-bit processor with a single-issue pipeline. The core is highly configurable, and you can configure items such as cache sizes and cache policy, and configure to have MMU and FPU and so on. The processor is available in a fault-tolerant version, where we protect on-chip memories from single-event upsets. It allows to maintain correct operation in the presence of correctable errors, and when an uncorrectable error is detected, we immediately stop, so that error will not propagate in the system. So next slide, please. What we see here is the GR716A, which is a microcontroller component based around a fault-tolerant LEON-3 processor. And this microcontroller is one of the main target systems for the new Zephyr LEON port. The microcontroller has EDAC-protected on-chip RAM with a capacity of 192 kilobytes. And it contains peripherals catered towards space applications, such as SpaceWire, CAN, 1553, EDAC controllers, and memory scrubbers. Next slide, please. And next slide again. And one more. Thank you. So, to the Zephyr part. Zephyr is a real-time operating system designed for resource-constrained embedded systems. It provides preemptive multitasking in a small footprint kernel, where resources are generally statically allocated. The memory footprint for small applications is in the order of tens of kilobytes. So that's where we are. There's a rich API available for application developers with some concepts familiar to users of Linux and POSIX environments. And Zephyr also provides advanced features, for example, kernel user separation and symmetric multiprocessing. But these features are not mandatory. So, and for the LEON port, we have not yet adopted the kernel user separation and the SMP support. Next slide, please. Zephyr employs a community-based development model where the development takes place on the GitHub platform. The source code is licensed under the Apache 2 license and allows free use in commercial and non-commercial solutions. In the picture to the right, we can see some of the members of the Zephyr project organization, which cover silicon vendors, service providers, product developers, and research institutions. The Zephyr project has well-defined processes covering code review, releases, quality, and it also organizes working groups on different topics such as API and testing and tool chains. And I would like to take the moment now to say that Cobham Gaisler is currently not a member of the Zephyr project organization, and I am not an official representative for the Zephyr project. Also on this slide, we have part of the release schedule. So we can see that in just a few days, version 2.5.0 is planned to be released. And there is also a long-term support release planned for later this year. Next slide, please. Zephyr can be seen as an application development environment where the multi-threaded kernel is one of the components. In addition, Zephyr provides a software development kit with compilers, libraries, and emulators for its various target platforms. The build system is based around CMake and it allows for building the kernel together with the application. Official user documentation and the kernel reference is available online. And there is a link on this slide which I can recommend if you want to know more about the capabilities of Zephyr. And the documentation is also maintained in the source code tree. So it's very convenient to keep the documentation close to the implementation. So next slide, please. And next again. And one more. Yes, so our work on LEON support for Zephyr RTOS started in early 2019 with a master thesis project. We had a student with us who implemented a fully functional port for the GR716A microcontroller. The port was not upstreamed to the official Zephyr repository at that time. And jumping forward to June 2020, Cobham Gaisler was awarded an European Space Agency contract for the development and validation of a new LEON 3 microcontroller for space applications. And the new microcontroller will be named GR716B, and it's an update to the microcontroller mentioned earlier. The updates include higher overall performance and added features such as CAN-FD and a spacewise router and improved ADC performance. One part of this ESA activity is to provide a software runtime environment for the new microcontroller. So based on our previous experience, we proposed to ESA to go for the Zephyr RTOS in this activity. And that was also well received. Next slide, please. So in September 2020, we revisited the Zephyr LEON port that we had locally here with the goal to update it and to submit it to the official repository. And 2 months later, the community review process was completed and the LEON port was accepted. What this means for the end users is that LEON is now an integrated part of Zephyr. You can download and explore Zephyr on LEON hardware or in a simulator. Next slide. And next slide again. Yeah, so I will now go over and say some things about the LEON port implementation. At the architecture level, we have added the Spark support. which was previously not available in Zephyr. It includes items such as exception handling and thread context switching. And this part is mostly implemented in assembly code. We support thread local storage, and that is a feature which allows for global variables to be allocated on a per thread basis. And one typical use case for this is the errno variable, which is defined by the C standard library and should be available for each thread. And FPU support can also be enabled per thread, and FPU context is saved and restored together with other task context at context switch time. So next slide, please. On the system on chip level, we have the implementation of items which are LEON specific, but which are not part of the architecture specification. This is where we find device drivers for interrupt controller, low-level clock driver, and UART, for example. Next slide, please. There are currently 3 board descriptions for LEON in the Zephyr 3. The QEMU LEON 3 board is used primarily for running tests in continuous integration. This board is probably the easiest way to get started because the emulator is distributed together with the Zephyr SDK, so it's highly available. The next board up is the generic LEON 3 board. And that board description is designed to be compatible with the FPGA example designs, which are available in the GPL version of grlib. So the idea here is that you download the grlib GPL version and pick a bit stream for the FPGA development board that you have. You program the bit file, build your Zephyr application, load it with grmon, and then you continue the development from there. And we also provide support in Zephyr for the GR716A mini development board, which you also see on the slide here, down to the right. It's a microcontroller development board, which is available. Next slide, please. Zephyr comes with an extensive test suite, which covers the kernel and various subsystems, such as the network stack and the drivers. These tests are run as continuous integration in the GitHub flow and are executed for each source change request. The number of tests executed is in the order of several thousands over multiple platforms, which now also includes the LEON. A key feature of the test infrastructure is that you can try your proposed kernel code changes locally on all platforms in emulation before submitting changes to the main repository. Next slide, please. So, and now on to some experiences and contributions back. Spark is the first big endian architecture in the official Zephyr source code 3. So as we started out, we were prepared to face a number of issues related to NDNS, but it turned out that there were just only a few of these. Another item where Spark differs from other Zephyr architectures is in the alignment enforcement on CPU level. On the Spark, all 64-bit objects need to have 8-byte alignment. And that is a requirement by the architecture specification. Next slide, please. And this leads to some of the contributions. We did detect and fix a number of Zephyr bugs during the LEON work, primarily related to portability. 7 of these items were related to big endian issues, and 4 were related to alignment issues. All the items were detected by running the Zephyr test suite on LEON, and all of these issues have now been fixed and contributed back. So in this way, the development of the LEON port has contributed to improving the overall Zephyr portability. And another conclusion is that the Zephyr kernel and major subsystems have now demonstrated to be endian independent, and that includes also the network stack. Next slide, please. Until now, the focus for the Zephyr port, for the Zephyr LEON port, has been on the low-level architecture support. And going forward, the focus will now shift to implementing device drivers with the GR716 microcontrollers as the primary targets. Zephyr provides stable APIs for different classes of peripherals, and a few of them are listed on this slide together with the corresponding peripherals in the GR716 microcontroller. However, some of the communication interfaces which are commonly used in space applications are not covered by the Zephyr driver API. So for example, there is no abstraction in Zephyr for space wire controllers or 1553 or memory scrubbers. So the current outlook from our point of view is that drivers for these peripherals can be provided outside of the official Zephyr repository, and that will probably be done by us. And next slide, please. We have identified some opportunities to improve and optimize the LEON Zephyr port. A few of them are listed on this slide, and I will not go through them in detail, and I will say that these are not critical for functionality. It's more nice to have features. So next slide, please. Yes, so we are also adding Zephyr RTOS support for our second processor line, the NOEL-V RISC-V processor. And the main focus will be on the 32-bit NOEL-V in the smaller configurations. But yeah, this could in principle also scale up to the 64-bit configurations as well. Both LEON and NOEL-V systems implement peripherals from the grlib IP core library. So the idea is to be able to share device drivers between the platforms. For now, the UART drivers shared, for example, and that has been working very well. No changes have been needed to be done in the source code, for example. So it just works. Our plan is to make an attempt at upstreaming the NOEL-V support during the first half of this year. Next slide, please. Yeah, so for the summary items here, Cobham Gaisler has contributed with a LEON port to the Zephyr real-time operating system. That's the main theme of this presentation. And yeah, Zephyr has a small footprint, which is an enabler for multi-threaded applications on the GR716 microcontroller. And the Zephyr LEON port will be further improved as part of an European Space Agency activity for the GR716B, which was mentioned before. And we also believe that the newly added LEON support can help bringing new application areas to the Zephyr RTOS. And that ends my presentation.
All right, great. Thanks, Martin. We have a couple of questions that came in, and I also encourage folks to start entering their questions in the Q&A while we're answering these couple. So first question from Stanislav. So what would you say are the notable differences between Zephyr and RTEMS, for example?
Yes. So I would say they match different segments, hardware or application segments, where Zephyr focuses a lot on the low footprint. That's one of the key parts. Whereas for Artemis, I'm not saying that Artemis is not focusing on footprint, but Artemis has other goals like the POSIX compliance and the SMP support. So for SMP support, I would say the Artemis support is, according to my knowledge, more mature with the fine-grained locking and clustered scheduling, for example. I think there is some work to do left there in Zephyr. So those are a few items.
Okay. So next question, are there other RTOSs envisaged to be supported?
Yeah, I think this question is towards the GR716, if there are other RTOSs envisaged to be supported. And currently, the Zephyr is the one that we work on and that we support, so to speak, as a silicon vendor. So yeah,
okay.
For now that's
okay.
it. We also provide bare metal environments for the microcontroller, which has been available for a number of years already.
All right.
And that is I would say that's a full environment with drivers and so on, but the limitation is it's single threaded.
All right. So next question, maybe a little more elaborate from Kirthi. So what is the code size for Hello World example under Zephyr versus the same thing under Artemis, assuming similar, same compiler flags? Doesn't have to be accurate guess, just the order of magnitude. From what I have vaguely investigated, we could say Artemis is on the order of 100 to 200K, while Zephyr might be on the order of tens of K in binary size. Is that accurate? And then I could imagine that Joel might want to, if he's got any clarification on that too. But why don't you go first?
I choose to not comment on the Artemis numbers because I'm not up to date on that. For Zephyr, I would say small applications without much logic would be in the order of tens of kilobytes. I mean, 20 kilobytes or less. But I mean, it's a hard question to answer because what doesn't make much sense to have a hello world program here. You don't need a real-time operating system for that, or even preemption and so on. So, but I mean, it's an interesting question. But it's the answers often. I mean, the answers are typically like a bit hand wavy, I would say. But under between 10 and 20 kilobytes for the Leon, I would say something like that.
Okay. And so Joel did chime in the chat. So the Artemis size depends a lot on the BSP. Last time he looked, it was usually in the 50 to 70K, but a lot of that was in the standard IO related libraries. Some of the VME BSPs can be a lot bigger due to bus setup. All right, probably have time for one more question if anybody has one for Martin. All right. And so again, if any additional questions come in, we'll take those over in the Slack channel. And as always, please, everyone, presenters and attendees, feel free to continue the conversations over there. Thanks a lot, Martin. Excellent presentation.
Thank you.